Hello, welcome back. Now that you have been able to pull in someone from your neighborhood and accurately and with detail explain to them what is happening, I want to spend about the next 15 minutes, 20 minutes, not much longer than that, just kind of going over how does this all relate to the paper readouts that we see. In other words, how does this relate to the echocardiograms? When you go into the hospital and they hook up the heart monitors to you and you see that beep, beep, beep going across the screen there. And so the first thing we need to do is understand that there are really three parts to a EKG readout. The first of that is the P wave, and then we have the QRS complex, followed by the T wave. The P wave, which is located or represented on the EKG by that first little blip that you see coming up on the screen, simply means that the SA node has fired, and it's going to fire or is firing to, again, throughout the right atrium over to the left atrium as well as down to the AV node. When we say atrial depolarization, we mean the action potential has begun. And so threshold has been met, and that's what you're seeing there with the P wave. The QRS complex, that is being represented right here, simply means that now the ventricle is depolarizing. In other words, the ventricle is getting ready to contract. Contraction doesn't actually happen until after the S with the QRS complex. And so the action potential has spread from the AV node over into the right and left bundle of His down to the Purkinje fibers. And so that is what you are seeing being represented there with the QRS complex. And then we enter into ventricular repolarization with T, or the T wave. So the ventricles have contracted, and now they are entering into a period of repolarization. The repolarization would happen basically from here on over to there, highlighted in the red. And so the T wave is going to represent the finishing of the contraction found within the ventricles. And so looking at this, you can see exactly, again, relating each of those parts, the P wave, the QRS complex, and the T wave, to what is happening within the heart. One of the things that I do want to just kind of point out to you is that when you go from basically P wave to P wave, you have yourself one completed cycle. And I don't know why I did that in red. That's horrible. Hold on 1 second. Again, it's from P wave to P wave. You have yourself one completed cycle that has taken place. You can also go from R to R and get the same thing. And so through this, from either measuring P wave to P wave or R peak to R peak, you could actually begin to time out using just the EKG what the heartbeat is. And again, that's going to vary whether it's a normal heart rate or when we talk about increased or fast heart rates, we call that tachybradia. And when we talk about slow, we are talking about bradycardia. All right, and then irregular heartbeats are, well, they're just irregular. Either way, what we are referring to here when we talk about tachycardia or tachycardia, this here is not correct. My apologies. Not tachycardia. Someone's probably yelling at me right now for that. What I meant to say was tachycardia. Tachycardia would then be the fast heart rate, right there. And then bradycardia is the slow. But either way, whether referring to tachy or brady, it is what we refer to as a arrhythmia. So an arrhythmia is a irregular heartbeat. Just kind of going back and touching on this, you can see the P wave, again, is represented by atrial depolarization. So the SA node is fired to the AV node as well as to the other atria. The left atria, I should say, as well as throughout the right atria. With the QRS complex, right there, we see a spreading of that to not only the Purkinje fibers in the ventricles, but we also see that spreading from the AV node down into the AV bundles. And then within the T wave, we see ventricular relaxation, pretty much. And so that's what this is all referring to picture-wise. And you can kind of relate that back again into the picture here. One last little thing that I will mention about this, and pretty much I want to focus on this bad boy right here. Because everything's going to come down to, when we start getting in a little bit more deeper into Chapter 20, epinephrine and norepinephrine, and how exactly they play a role in the regulation of the cardiovascular system. In other words, how epinephrine and norepinephrine plays a role in how fast that SA node is going to be firing, or how slow that SA node will be firing. In conclusion, I want to spend just a little bit of time talking about anatomy of the blood vessels. Basically, we have three layers that we need to be concerned with. The most inferior level is the tunica intima. I suggested that you remember tunica intima, as in that it gets nice and close and intimate, if you would, with the blood and the fluid passing through the arteries, arterioles, capillaries, venules, and or veins. So the tunica intima is the one that is the deep layer. It is composed of simple epithelial cells. And the question is why? Why would we expect epithelial cells, endothelial cells, if you would, to be lining or made up of, or making up that tunica intima level? And the answer always comes back to one simple answer, and that is diffusion. The epithelial cells will allow oxygen to diffuse across. It will allow carbon dioxide to diffuse across. It will allow ions to diffuse across. It will allow water to diffuse across. It all comes down to diffusion for the tunica intima. The middle layer is the tunica media, and this is typically the largest layer that is found within blood vessels, whether it's arteries or veins. Within arteries, we see a lot more greater amount of elastic connective tissue because of the variance that we see with pressure. And typically within veins, you see a whole heck of a lot less elastic tissue, but you see more smooth tissue, specifically smooth muscle tissue. And then tunica externa, this would be the most superficial or outside layer of the blood vessels. And again, the purpose of that is to help to attach to surrounding tissue so that the blood vessels aren't just free floating in the body. If the blood vessels are going through the heart, what you're going to simply see, or I'm sorry, not through the heart, but through muscle, you're going to see that loose areolar connective tissue of the tunica externa attaching to the loose areolar tissue that is surrounding or creating the bag surrounding the muscle. Just a couple little bit of tidbits of information. When we talk about the capillaries, understand that we have very low pressure within the capillaries, and the reason for that is because as that blood is traveling down the arteries or the arterioles, and when it reaches the capillaries, there are so many capillaries. I mean, thousands of square feet of capillaries that blood disperses into all of those capillaries and reduces the pressure of that blood that is coming down the arterioles, and that is the only way that the body has developed to really handle or effectively deal with that incoming pressure. You spread that pressure out over a greater area or a greater surface area, and overall it reduces the pressure. Otherwise, you'd be blowing capillaries left and right, and that would not be a good thing. A couple mentions of the veins. They tend to have a little bit larger of a diameter. They tend to have elastic connective tissue within the tunica media, and then a minimally ability to constrict. Oh, I'm sorry. This here is actually not as accurate as I would like it to be. While they have connective tissue within the tunica media, it tends to be less connective tissue than what we see within the arteries and arterioles. And then we have this little diagram here, which I invite you to print out. You can see it has a nice little breakdown and description of your arteries, your arterioles, your capillaries, your venules, and your veins. As you increase downward, of course, and then back up again, you're realizing that your veins are changing size, so that your largest vessels that you have within the body are your arteries, and then smaller diameter would be the arterioles. Your smallest would be your capillaries, and then you begin to increase in size again with your venules, and then your veins as they lead back into the heart. And so again, I would suggest that you print this one out, put this into your notes so that you have it readily available for you to study from. And then there's this really bad picture here. Again, the only reason why I give this to you is because I want you to see this here is where your connective tissue would be within your arteries, and compare that same level of what would be supposedly connective tissue within the veins. And you can see the vast amount of difference that there is. Same thing with your medium-sized veins, or and then your medium-sized arteries over here. All right, and so forth and so on. You have a lot more elastic tissue associated with your arterial side, and again, pressure is greater. And so with that, I said this would be a quick one, 15 minutes or so. I don't even know if we hit that long. I would go back and really focus in on the second of these WIMBA sessions, where we begin to link everything together for this. As always, happy studying, and please let me know if you have any questions. Shoot me an email, or feel free to jot it down and ask me during the next lecture. Until then, happy studying, and we'll see you when we see you.